Hello, in this video we're looking at writing basic trig values. So that's when I would ask you, hey, what's sine of 30 degrees? Hey, what's sine of pi on 4? What's cos of pi on 3? Or what's tan of 45 degrees? And I would just expect you to know it. And this is for learning intention 17. And this is the table you have to memorize. You should know this from last year. What I want to do though is show you where these values come from. I'm very wary of just telling you to memorize this, and I want to see how easy it is to build two triangles with a bit of geometry and get all the information in here. So let's do that. Let's build two triangles. I'm going to build an equilateral triangle, which is a triangle with all equal sides. This was known to the ancient Greeks. They figured it out, and I'm going to construct it how the ancient Greeks would have constructed it. This is geometry. Unfortunately, it doesn't seem to get taught very much, even though it's on your curriculum. So this is a line segment, and an equilateral triangle has to have two other lines that are this exact same length. So what the ancient Greeks did is they constructed these with straight edge. So they had a straight edge, like a ruler without markings, and a compass. So I've got a compass here, and I'm going to draw part of this circle there. I'm going to move this circle over to this point, and I'm going to draw the other part of this circle there. Okay, there's a point of intersection there. What's special about that? What's special about that point of intersection? What's special is that that line segment here must be the same length as this one. Because think about it, imagine the compass keeping the radius constant as we go around. Because that's part of a circle, right? So that must be the same length. But hang on, over here we did the exact same thing. We got our compass and we swung the arm around here. There we are. There's an equilateral triangle. Constructed how the ancient Greeks would have. Next, we have to know that each of these angles are the same. So, well, each of the sides are the same. Because it's equilateral, each of these angles are the same. And they're all going to be 60 degrees. Well, they must be, because they're 180 degrees in a triangle. And if they're all the same, then they must be 60 degrees each. Why am I banging on about this? We're doing trigonometry. Why am I making an equilateral triangle? Well, if we call this length 2 units, that must be 2 units down here. That must be 2 units here. Now we're going to do something called bisecting. We're going to split that angle in half. And you can do this with straight edge and compass. I'm just going to eyeball it. So I'm just going to do it roughly, but you can do this precisely with a straight edge and compass. So we're going to split that angle in half. Alright, let's see. That's 60 degrees there. Or we can call that pi on 3 radians. Well, what's this? Well, that must be 90 degrees because it's perpendicular. So we have a 90 degree angle here. What's this over here? Well, it's half of 60 degrees because we've bisected or split 60 degrees in half. So that's 30 degrees. Or we can call that pi on 6. Well, this length here is half of 2. So that length is going to be, you guessed it, 1 unit, just there. Well, what's left? I want to know this length. I want to know all about this triangle. Well, let's use some Pythag. Let's call that length A. So we know that A squared plus B squared equals C squared. A squared plus 1 squared equals 2 squared. A squared equals 4 minus 1 is 3. A equals, and we can't really talk about negative length, so we're going to call it the square root of 3 here. Alrighty, so what you can do if you like, I'm going to do it because I can, is you can rub out this part. Don't bother rubbing this out. I just want to highlight the important triangle. You can rub out this part. You can rub out your construction lines that we used to make it. And you get this special triangle. Why is this special? Because you can find these values here. Let me show you. Alright, let's say you want to find sine of pi on 6 and you don't know what it is. Well, you just constructed a triangle. Sine is the opposite over the hypotenuse. You need to know that. Sine is the opposite over the hypotenuse. Let's have a look. Here's pi on 6. There's the opposite here, 1 unit, opposite, over the hypotenuse, 2 units. So sine pi on 6 is a half. And hey, look over here. That fits with our table. Sine pi on 6, or sine of 30 degrees, is a half. Let's try another one. Let's try cos pi on 6. What's that? Well, cos is adjacent over hypotenuse. So it's, let's see, well there's pi on 6, so it's the adjacent, which is root 3, over the hypotenuse 2. Alright, now we're really rolling. Look at that, where's pi on 6? Cos of pi on 6, root 3 on 2. Fantastic. So we've got a triangle to find sine, cos, and even tan of these values. Let's find tan of 30 degrees. Let's do it down here. So what's tan of 30 degrees? I don't know. Let's have a look. Tan's opposite over adjacent. So the opposite is 1 unit over the adjacent, which is root 3. Alright, because I'm a good student, I like to rationalize my denominator. So that means you make what's in a denominator not a surd. So I'm going to times the top and bottom by root 3. And that gives us, well, 1 times root 3 is root 3. Root 3 times root 3 is 3. There's our value there. You need to know that 1 on root 3 is the same as root 3 on 3. You need to know that these are equivalent. Let's see, what else? Shall we do one more? Let's do one more. Let's do tan of 45. Oh, well, there's no 45 degree angle in here, so we can't. Let's do tan of 60 degrees, or tan of pi on 3. Well, pi on 3 is here. Opposite is root 3. Adjacent is 1. So that's root 3. Alright, root 3. Great. Well, we've just discovered a triangle that lets us find these values here and these values here. What about these ones? And what about all the rest? Well, I'm going to leave all the rest to you. That's to do with the unit circle. But we're going to go through how to find these ones. To do that, we're going to construct a triangle that is isosceles. Isosceles means it has 2 lengths that are the same. So let's construct an isosceles triangle. Alright, so if I use my compass, I'd swing it around here to get a line of the same length. So I could use a straight edging compass to make sure that this line is the exact same length as that line there. See, because I could swing the compass arm around there. And then finally we're going to add the hypotenuse. Hypotenuse actually comes from the Greek word to mean tension. So it literally means like a piece of string, like tensioned across 2 things, 2 arms. Alright, there we go. There's our isosceles triangle. That length is the same as that length. Well, by symmetry, you can see that if I draw a line there, it's symmetrical across that line. So that angle must be the same as that angle. That's a rough kind of proof to say it. You can do it more formally. Nonetheless, that's going to be 45 degrees. That's going to be pi on 4 here. 45 plus 45 is 90, plus another 90 is 180. It works out. Alright, let's call this 1 unit. 1 unit. What's this length here then? Well, we use Pythag. So 1 squared plus 1 squared equals c squared. C squared equals 2. C equals the square root of 2. Alrighty, what's tan of pi on 4? Tan of pi on 4, well, that's opposite over adjacent, so that's 1 on 1, which is 1. Tan pi on 4 is 1. Beautiful. What about sine pi on 4? Well, sine is opposite over hypotenuse, so that's the opposite's 1 on root 2. And if we rationalize the denominator, that's the same as saying root 2 on 2. So you must know that these are equivalent. It's also the same as saying the square root of a half. All these are equivalent. If you ever see these, they're interchangeable. So these two triangles are very important. They allow you to find all those values. Even if you know all these values, it's good to know the triangles so you can know where they come from. If you don't know these values, it's good to know the triangles so you can derive them. It's interesting to note, this is for the special kids, it's interesting to note that if I tell you, and you'll have to know this for later, if you're doing specialist maths, if I told you the value of sine of theta, if I said this is 0.2, that means you already can calculate the value of cos theta, tan theta, sec theta, cosec theta, oh I forgot how to write sec, cosec, cosec theta, and cot of theta. You can find all 6 trigonometric values just from knowing these triangles, from working from triangles essentially. That's just a side note, and if you have been, thank you for watching.